Hello everybody. Today we're going to be talking about our project 1 and we did the turntable problem, and my name is Chad Schmidt and you'll be meeting Jack and Austin later in the video. For this problem, we are given a turntable with a radius of r. A box is located on the outer edge of the turntable with a mass and it is known as m1, which has a constant angular speed. There is an ideal string that is attached to the box. Then it heads to the center of the turntable where a massless pulley is located. The ideal string then runs through the massless pulley and then down and through the middle of the table, then connects to our hollow ball with a mass. The ideal string also wraps around the hollow ball several times as well. What we are trying to find is the angular speed of the turntable. The equations we'll be using is our net force equation, which is known as F net is equal to the mass times acceleration. We also are using our net torque equation, which is known as T net is equal to the force times radius times sine theta. These equations shown above are configured to work with this problem. Taking a closer look at our equations, we can see our force of gravity minus our normal force, which should equal 0. Our tension force of the block is equal to our net force, which is also equals to the mass of the box times the acceleration of the box. Then our force of gravity minus our tension force of the hollow ball equals our net force, which is also should equal our mass of the hollow ball times our acceleration of the hollow ball. Then our net torque is equal to the radius times the tension force. That then equals our radius times the tension force times sine theta, or sine pi over 2. These equations will go further in depth later on in the video. Some assumptions that we can make about this turntable is that it is a frictionless table. So we don't have to include a friction force or any other forces that involve friction. The pulley is also massless, so we do not account for the mass of the pulley. And once again, the angular speed is constant on M1. So there is no change in our constant speed of M1. Then we can look at our diagram. This is just a small explanation of what is happening that I explained earlier in the video. I have added our free body diagrams of the mass of the box and also the mass of the hollow ball. And as we can see, we have our normal force heading upwards. Our force of gravity is heading downwards. Then we also have our force of tension that is heading towards that pulley. We then, on our hollow ball, have a tension force that is heading upwards, that is going towards the pulley, and also we have our gravity force that is heading down. And the systems that we're using in this equation would be our force system, of course, and also our motion of rotational and translational, and also we're using our torque system.
My name is Austin Cates, and I'll be taking care of the calculations for this problem. First, we can kind of separate it into two separate systems. We have the box, which has a net force equal to its net tension force, and we also have the ball, which its net force is equal to the gravitational force minus the tension force. This ball also experiences a net torque, which is equal to the radius times the tension force. In order to solve this problem, we also need some other relationships, which I have listed on the right. I will go over these into more detail in the following slides. We are going to start with the ball. Our main goal is to find the net tension exerted on the string by the ball. To do this, we need to find the translational acceleration experienced by the ball. To figure this out, we're going to relate our two net torque equations. The first one we have is the moment of inertia times the rotational acceleration, and the second is the radius of the ball times the tension force. To find the moment of inertia, we can look this up off of a table for a hollow ball, and this is equal to 2/3 the mass times the radius squared. The rotational acceleration is going to be equal to its translational acceleration divided by its radius. This is because for however much the ball travels in its translational, we have an arc length that is of the same magnitude. This gives us a net torque equation of 2/3 mass times radius times translational acceleration. For the second equation, we will be using the net torque is equal to the radius times the force of the tension. And this we can just plug in. After solving for A2, we get that 3/5 of the gravity is equal to its translational acceleration. Finally, we can plug this back in to get our net tension force is equal to 2/5 the mass times the gravitational acceleration. We will then use this relationship with the system of the box in order to figure out our angular velocity. Next, we'll be looking at the box. Our main focus here is to get omega in terms of our knowns and our tension force that we previously solved. To start with this, we got our net force is equal to our tension force. Because the box is rotating on the turntable, its acceleration is experienced as the centripetal acceleration. This is known to be velocity squared over the radius on the turntable. Plugging this in, we find that our tension force is equal to the mass times velocity squared over the radius. Using velocity is equal to omega times r, we can find that the tension force is equal to the mass times the radius times omega squared. Finally, we can solve for omega, which is equal to plus or minus the tension force over the mass times the radius. Using the tension force we previously solved for, we find the solution is equal to omega, which is equal to 2/5 the mass of the ball times gravity over the mass of the box times the radius on the turntable. The plus or minus here represents that the table can go either clockwise or counterclockwise as long as the magnitude is equal to omega, the box will stay on the table without moving.
Alright, my name is Jack Hayhurst, and I will be doing the sense making and the reflection for this problem. So, just doing a quick check of our units, we have our final answer, and those units equate to be kilograms times meters per second squared over kilograms times meters. You can cancel out the kilograms, you get meters over second squared over meters, and then through multiplying that out, you get meters over meters times second squared. Then you can cancel out the 2 meters, you get 1 over seconds squared, square rooted, which gives you 1 over seconds, which would equal radians per second. So here we are doing some more sense making. We're going to make one of our values 0 and see how that affects our final answer to see if this makes any physical sense. And so by setting m2 equal to 0, which is the mass of the ball, it no longer has a downward force at all. Therefore, it would make sense that the angular velocity is 0 because there's no force on the system. So some of the different aspects of this turntable question are familiar from past problems we have done on our either homework or in studios or even in class. The first of these problems that are related to this project is this problem from homework 0. The reasons it's similar is it has a pulley with no mass, as well as object. The mass 2 in this problem is pulling down, causing the mass 1 to move over in theory. But this problem uses translational motion instead of angular motion like the problem for the project does. So now for the next similar problem, we have this problem from homework 3, which is nearly identical to that of homework 0. The difference between this and homework 0 is this pulley does have a mass, and as a result of this, it wanted us to find a value for the pulley, so we actually used rotational motion to solve this problem. The differences from the project is the project pulley has no mass, and also, just like homework 0, it's 2 blocks. Block 2 would be a ball with a string wrapped around it in respects to the problem, but that is not the case here, so there's a difference between this problem and our project. And the final problem that we will compare to our project is this problem from Studio 4. It has 2 wheels, both are traveling downward. Wheel A is wrapped around much like the ball in our problem and is unraveling. The unraveling force causes the tension force to let wheel B go down. So one big difference here is in our problem, we have a ball falling, but the other box is up on top of the turntable, so it is not falling downwards. It is being pulled to the right, or could be pulled to the right. The other difference is we don't actually have anything that says this pulley is massless in the problem. We had to account for mass, so there's another difference with the problem for our project. And that wraps up our Physics 212 Project 1 turntable problem.